Depilatories or hair removal. This lecture took place on Friday the 22nd of March. Now I'm really going to concentrate on the hair removing creams because they are the most complex. The wax strips are very straightforward products. They're just an adhesion system. The hair lightening products are basically a bleaching system. So the concentration is really going to be on the actual hair removing creams. Right. Oxidation, the addition of oxygen, removal of hydrogen, process of electron loss. Why do we talk about this for a depilatory cream? Well, because this actually will help us describe the processes at work that go on in the cream, and this language will actually assist us more in understanding how that cream works and why it works at a basic level and what we can expect from its behaviour when it goes wrong. Now we'll just describe these two processes. Oxidation, very simply, addition of oxygen, that's everybody understands that. Iron rusts, so solid iron goes to iron oxide, addition of oxygen. Removal of hydrogen is more difficult to think about, but perhaps one good example is think of getting vinegar from ethanol. So you've got an awful lot of things like white wine vinegar and malt vinegar, and they all start from actually ethanol, and if you remove enough hydrogen from the ethanol and add one oxygen to it, you end up with acetic acid, which is of course had some hydrogen removed, and so that's a nice thought process around oxidation, because basically you're blowing air through ethanol and eventually you end up with vinegar. And then we have this process for electron loss. If we go back to our idea of the iron rusting, you start with a neutral iron atom and that goes to iron 3+, so it's actually lost electrons to the oxygen. And you can also think of this as an increase in the oxidation number. So again, if you think of iron rusting, iron will go from neutral atom to 3+, so it's a gain of in number, it's going to 3+. Reduction, if we go through the removal of oxygen, because it's basically an opposite of oxidation, so you're taking iron oxide in the form of rocks and put them through a blast furnace and they come out as iron metal, and that's removed the oxygen from them. Addition of hydrogen, you can think of things like margarines being produced from unsaturated fatty acids having hydrogen placed on them, so you lose that unsaturated grouping, and so those now become that's the addition of hydrogen, and you talk about that being a reduction. You could also think of the reverse process of reducing, say, acetic acid back through to ethanol. You're actually adding more hydrogen to it. And finally, you can think of the process of electron gain. This time, if you think of oxygen in terms of the rusting of iron, that's actually gaining electrons and that's been reduced. And you can think of reduction again as a decrease in the oxidation number. That's going from, the oxygen is going from neutral to 2-. Now you often see these little equations associated with redox processes. In this case, what we've got is hydrogen peroxide plus electrons is going to a hydroxide ion. Okay, and then we think of the ammonia in this case reacting with a hydroxide, and that's forming a neutral ammonia dissolved in water in essence. So what we're seeing here is hydrogen peroxide gaining electrons, so that is actually a process of reduction that's happening there. So we can think of the hydrogen peroxide being reduced, but it will be oxidizing another molecule. Now, this idea of oxidation and reduction comes in very nicely when we start talking about hair lightening creams, because they're often sold with depilatory products, and in essence what you're making is a bleaching agent. And as you can see, I've highlighted the ammonium hydroxide and the hydrogen peroxide, the very components we had highlighted on the previous page. And what's happening there is you are creating a system which oxidizes, and what you're hoping to do is oxidize any dye that's actually in the hair, and that's going to be produced by the melanocysts at the bottom of the hair roots. So you've got melanin in the hair giving it colour, and what you're doing is adding electrons to that and actually destroying the colour by this process of oxidation. Now, what you've also got is this process that is making a cream here. So you're trying to have something which will actually stay on the skin, and these are what the other reagents are doing in there. You've got to sometimes break down a formula into sort of what are the steps that are happening, what's the chemistry that I need to do, and then what's the physicality that I need. In this case, you actually need the formula to stick on the skin, so you have to have something that will allow it to do that, and that's why you have these cream components. And then you have to actually remove that fairly quickly, because you don't want something oxidizing the skin for any length of time. And again, washing, please if ever any of you use these products, please make sure you do a good job of removing the cream. It will penetrate the hair cuticle if you've got lots of bleaching agent there, and so that's going to keep the hair coming out for a while as a sort of lighter colour. Okay, I thought it would be a good idea to just look into the structure of hair again. Now, the main protein that's responsible for the structure and all the properties of hair in terms of being able to sort of flex and having strength and rigidity to it and elasticity, that's all really down to this protein called keratin. And keratin is an amino acid sequence, and it's made up of these different amino acids. This is what the analysis of keratin from humans has shown in terms of the amount that's present, and we'll just look towards what's special about those amino acids. So cysteine is particularly special because it's got this SH group on. It's the let's just put on the pointer, laser pointer, so you've got this SH, and that's actually very important, and we'll come to that a little bit later. But then you've got serine, and what you've got on there that's actually a little bit different is you've got this OH group on here that's making that really quite polar, and it also makes it quite good for actually forming hydrogen bonds too. And then you've got glutamic acid. Now, where's glutamic acid? Well, we've got glutamine. I'm sorry about the naming being very slightly different here, but what you've got there is you've got this amide grouping going on here, and again that's very polar. That's going to be really terrific for forming hydrogen bonds with. And finally, you've got proline, which has this net positive charge on here, and so you can actually again form ionic bonds within the hair molecule itself, and that will give it a shape and structure as you have attraction between individual parts of the hair molecule. Now, this is a slide which I've shown before, but I really can't reiterate it enough. You've got this position within the amino acid sequence or chain where the bonds can actually rotate, and when they rotate they can allow the overall chain to take up almost any position. It's almost like thinking of a piece of string. That's just got certain steps on it that you can then allow it to rotate and take up any conformation that you want, but it does have some restrictions on it, and the restriction really is around this carbonyl group and amine here, and those will tend to be planar in that aspect there, but then this carbon atom and the bonds to there on either side, those can rotate, and so you can get that any conformation is possible occurring. Now what you also get is, we talked about this a moment ago, we talked about the ionic bonds that can occur, and you can also talk about the hydrogen bonds that can occur, and you've then got slightly more complex interactions. You have the interaction of, say, the aliphatic groups. Those are water hating, and so those will tend to interact with one another rather than interact with anything that's more hydrophilic and wants to be around water. So what you will find is that if you look at this, you'll see that these non-polar side chains, the aliphatic groups, quite often they're all trying to be turned inwards, whereas all the polar sides of the chain are trying to be outwards. So we get this folded conformation. So there's a number of aspects that are at work on how a protein will fold itself. And then finally we've got this SS bond that can occur. Sulfur is somewhat infamous for this, in that what you can get formed between the cysteine amino acids by carrying out a process of removing hydrogen, so that's the oxidation, because it's the addition of oxygen, removal of hydrogen, we actually form this SS bond. Now it's a weak chemical bond, so it actually becomes quite a good target to hit in terms of trying to break down the structure of the hair, because it's, like I said, a weak chemical bond, and we can target it through this oxidation reduction processes. So again, we've got the protein structure. I'm just trying to highlight that a little bit further, and what you're seeing here is this idea of the disulfide bond occurring within a strand or polypeptide backbone, and you can actually see that the SS bond, so we've got here disulfide bond, but we've also got an ionic bond trying to hold that structurally together as a peptide backbone, and here we've got two alpha helices, which is basically the structure that you see in keratin, is alpha helices, and those two are bonded together by these disulfide bonds. So that's really saying that we would expect that those two pieces of amino acids, those two strands of amino acids that are forming these alpha helices, to actually go around together, and it's those two bonds that actually hold them together. And if you attack, like we said, those are weak bonds, so if you were to attack those, the two strands should come apart. Now, urea is also added to a lot of hair removing creams, and it's got this property of helping to actually straighten out or unfold a protein structure. We have to remember that proteins are complex 3D structures, and it disrupts the non-covalent interaction. So it's not actually acting on those sulfur-sulfur bonds, it's acting on a lot of these other bonds that we're talking about, the ionic bonds in particular, and the hydrogen bonding as well. So it can help to unfold that polypeptide chain, and we can think of that polypeptide chain essentially unwinding and having lost its ball-like structure, or it will actually become easier to break down after adding urea to it. Historically, urea was used in leather softening and often in cleaning clothes as well, because it had this property of actually helping to unwind proteins and actually remove dirt. Now we've also got this energy bond energies here, and you can quite quickly see how the carbon sulfide bond is actually quite a weak bond in comparison to many of the other bonds. Now, what happens when we use our hair removing cream? Well, the main ingredient is always going to be this thioglycolic acid. Now, it might be added as potassium thioglycolate, but the reason for that is it's not trying to deceive you. It's because it's got these different ionizations, and the different ionization levels we can actually talk about with the Henderson-Hasselbalch equation. That's always great for exams and for essays. And where we get that from is we think of our acid plus water producing a conjugate base and a hydronium ion, and we can put those concentrations into an equation. So we have a concentration of our conjugate base over our acid itself. If we take a log of that and then add it to what we call our pKa value, we can end up with the pH. So this allows us to predict what the pH will be for given concentrations, and what it means is that we know the state in which the thioglycolic acid will be in at a known pH. So now we've got this pKa of 3.83. So what that means is we're seeing a really rapid change in pH for every unit of sodium hydroxide we add to that acid. To neutralize it, it suddenly goes very little change, and suddenly very rapid change, and then it goes back to a period of very gradual change, and we get our second ionization occurring with a pK of about 9.3. So what we're seeing is our first ionization ionizes the carboxylic acid group, so we get it ionized, and we have potassium, so you've got potassium thioglycolate, and then you actually get an additional ionization of the sulfur hydrogen grouping, so you actually get that changing to form a sulfide minus ion. So that's actually doubly ionized now, so that's taken a lot of sodium hydroxide to get it to that point. Now what it means is to keep it in that state where you've actually got this sulfide minus grouping on, takes a lot of alkali, because it has to be maintained at this pH 9.3 or greater to actually ensure that the thioglycolate is in this form, because it's only in this form that it can actually interact with hair and start breaking down the sulfur-sulfur bonds that hold the strands of keratin together. So that's the real key to this, is very high pH is required to doubly ionize the thioglycolic acid to dipotassium glycolate, thioglycolate rather. So sources of high pH, well, the most obvious one is sodium hydroxide that I showed in the last graph. Now that's very soluble and completely dissociates. So a lot of the time we start thinking about solubility product and how you can talk about pK, and it's kind of not applicable to sodium hydroxide because it is just so soluble, and you can pretty much work out what the pH is going to be for a given concentration. It's really quite straightforward. So for a pH of 12.5 is 0.03 molar or 1.26 grams per litre. So you've literally got a very straightforward translation using that Henderson-Hasselbalch equation for sodium hydroxide. Now, calcium hydroxide is really quite different. Here you've got the solubility, it's got a very definite solubility, and it isn't very much. You've got less than 2 grams per litre solubility. Now, we actually talk about a solubility product. Now, that's actually a very low solubility product, and what that indicates is that it's very difficult to get that into solution. However, it has an extremely high pH. So what we've got is our OH minus ions are being created in solution. There aren't that many of them, and they're very limited. But the maximum pH we can get from this is about 12.5. So what's happening when we add our thioglycolic acid to hair? Well, what you're seeing is the cysteine disulfide double bond is been broken, and it's bonding with the sulfide component of thioglycolic acid. So what we see is our cysteine unit here, and then we've got our thioglycolate there, and that's freed up our cysteine. So it's literally going onto the hair, attaching to the hair, and it's breaking up the hair structure, because instead of being bonded keratin to keratin, it's been bonded keratin to thioglycolate. It's always a good idea to just have a quick look at the actual safety status of these substances, and thioglycolic acid and its salts can be used in up to 8% for professional products. The actual consumer product is much lower. Hair rinse off products, maximum concentration allowed 2%, pH up to 9.5. Depilatories products, they're allowed at maximum 5% and a pH of 7 to 12. So they can't go above the 5% level for that. That's a really good idea, because the more you actually end up putting the thioglycolate in, the more you end up having to have an alkaline product. And alkalis are very dangerous. They basically can dissolve up skin, they dissolve the fatty acid, form it into soap, and so you'll get a saponification occurring at the surface of the skin. So it's absolutely essential that these products are very, very thoroughly washed off. You cannot leave anything on of these products. So very simple summary: thioglycolate is likely to be used into the future. It needs a high pH to operate. High pH is damaging to the skin. It's an alkali burn. It's got to be removed by showering. It's the best way of actually removing that. It's unlikely to be surpassed by something. The older option was using sulfides directly, and that was used for and that's still used today for leather processing. They're incredibly toxic. You've really couldn't wish for a nastier product of being alkali and toxic in terms of leather tanning or leather processing for removing hair. So there's no way that that really can be translated into hair removal for a consumer product, because basically it would almost certainly kill people fairly quickly. And let's leave it at that.